Okay, so this is part D for PDC. So what we're going to do is going to explain how a cascade controller may be used to enhance the control of an exothermic reactor by adjusting the flow of makeup cooling water in the circulating cooling jacket. And then we're going to draw the block diagram and derive the transfer functions, and then simulate the unit step disturbance rejection. So, here. So I've already drawn our cooling jacket and reactor with our agitator. So what we're going to see is we're going to have a probe that's going to measure our T reactor, which will also have a set point for this set reactor. And then we're going to have a probe for our cooling water, which will also have a set point for the cooling water, which this is going to be connected to a controller, which basically feeds right back to a control valve. So I have this control valve, which is going to be representing the inlet to our cooling water, and this is going to be our cascade controller. So essentially what this is doing is the probe is going to measure the temperature of the cooling water, send it to the controller, and then feed it right back to the cascade controller to essentially control the flow of the cooling water inlet. So this is how that cascade controller is very important. Okay, so for our second part, what we're going to do is our basically our T set point of our reactor, which will be fed, I guess there'll be a controller here, which will input into our G reactor T control, be fed to our controller, which will affect our G jacket temperature control, which will affect the actual jacket, fed into a controller, which will feed to the G reactor. And then before we can output the temperature of the reactor, we're going to have 3 separate controllers here before we can reach that reactor. And why? Because if you think about our tank, we're going to be able to control the flow rate, concentration, and temperature of our feed. So we're going to have separate boxes for these. We're going to have our GQ, GC, and GT with an input of Q, C, and T. So this is basically what our block diagram looks like, and our controller here, oops, it's really bad. Our controller here will be basically talking to this one in terms of flow and temperature. Okay, so Actually, just go into this controller, and then our controller here will be regulating right there. So now for next step, we want to simplify this down so that we can start our derivation. So we're going to have our y set point as we set in part C, and so we go into our controller, which will feed to our GC2, which goes into a controller, to our GC1, which goes to our GP1, which goes to a controller, into GP2, which then we get our Y, and then inletting our controller is going to be our disturbance with D as inlet, and then our, I believe it's right there. I think it might be right there actually. Yep. So our controller would be regulating that point, and then our first controller would be regulating our outlet. So this is our block diagram, and then we're going to start our derivation. Okay, so to start off, we're going to define y as equal to GP2 times z, where z equals our disturbance times the disturbance controller plus GC1 times GP1 times E minus Z. Sorry, something in my mouth. And then Z, which equals 1 plus GC1 times GP1, which equals D times GD plus GC1 times GP1 times E. Now, what we're going to get is just Z equals DGD plus GC1 GP1 E over 1 plus GC1 GP1. Now, what we do have is this little mysterious E, which equals GP2 times Y minus Y set point. Now, if we plug that in, we get Z equals DGD plus GC1 GP1 times GP2 times Y minus Y set point, all over 1 plus GC1 GP1. However, now we have this Y that we want to find, so let's isolate that. So what we get is DGD, sorry, that's a D, times GP2 over 1 plus GC1 GP1 plus Y minus Y set point times GP1 times GP2 times GC1 times GC2, all over 1 plus GC1 times GP1. Okay, so now what we're going to do is make Y times 1 plus GP1, GC1, GC2. Also, it's 1 plus because the GP2 can be substituted out, making it 1 plus. 1 plus GC1, GP1, which essentially equals our DGD times GP2 over 1 plus GC1 times GP1 times D plus our GP1 times GP2 times GC1 times GC2 over 1 plus GC1 times GP1 times our set point. And then to basically finish this off, let's use white, we're going to count this as beta, this as alpha, this is also beta. So when we simplify this out, we get y equals alpha over 1 plus beta times d plus beta over 1 plus beta times y is p. And this right here is the equation we need for a transfer function. And now we can go to our coding. Okay, so now for the coding section, I'm going to simulate the unit step disturbance rejection and set point servo control for the following cascade control system. So I've already got our values that we need that have already been described. So to start, we're going to find our beta and alpha and put it in the code that we already found. So beta is the GC1 times GC2 times GP1 times GP2 divided by 1 plus GC1 times GC or GP1. This is supposed to be G, and to just double check, yep, that's it. And then for our alpha, this will be the GP or GD times GP2 over, so GD1 times GP2 divided by 1. Actually, I can just go ahead and copy this over. Don't need that comma. There we go. And then we have our T and Y disturb. Oh, also, for our inner loop, we're going to be looking at our disturbance, but our transfer functions are right here. So this one is for the disturbance, and this is for the reactor, and this can be relevant to what we do in 1 second with this. So if we do sim, our alpha divided by our 1 plus beta, which is what we just saw. This will be lambda t of 1 n equals 500, and then dt equals 1. And then, not dig, fig make underscore subplots, and fig dot add underscore scatter x equals t, y equals y disturb, mode equals lines, and then fig dot show. So there is our first graph. So now what we're going to do is, basically I'm just going to copy this over because it's pretty much the same thing. However, instead of looking at the disturbance, which is the inner set point change, we're going to be looking at the outer. So we just have a few things that are different in terms of beta. And then, of course, we got to look at the reactor, as mentioned in our little notes right there, which are transfer functions. So this should work. There we go. So our bottom plot that we just found is representing our servo, or our outer set point change, and the top is our disturbance in respect to our inner set point changes. And if we can, I think we can zoom out a little bit. Okay, it doesn't look that great, but I think we can look at the changes a little bit more better here. We can see that with the inner set point changes, our oscillations are around 0 or in between and going down to the negatives, and then we finally reach steady state at 0, whereas our outer, we are actually in the positives, and our steady state is going to be achieved around 1. And that concludes our part D. So thank you for watching.